In this video, I want to go through a CFA Level 1 exam style question on the computations necessary to derive modified duration, which is an extremely important, critically important measure in the fixed income section of your curriculum. So if this is something you want to get right in the exam, keep watching and let's get solving. So this is the question which I want us to have a go at. A bond with 3 years to maturity pays an annual coupon at 6% of par value and trades at a yield to maturity of 8%. The bond's modified duration is closest to. Okay, well, it's not necessarily the case that you will have to for sure compute modified duration in the exam. You may be required to use the duration measure to derive something else, or maybe show an appreciation of it, but your curriculum shows you the whole computation and you're supposed to be able to do it. So just in case you need to perform this in the exam, here's how we do it. It's not necessarily an easy process. It's not necessarily very quick, but I want you to be ready to do it. Okay, so what we're going to have to do is the following. We're going to have to compute modified duration, start with something called Macaulay duration. Macaulay duration. And from this, we'll derive modified duration, but don't worry, the adjustments which we'll need to do are going to be relatively easy. Now, one thing I need to do before we compute Macaulay duration or set up the whole framework is actually compute the value of the bond with which we're dealing over here. So bond price or bond value, which is not provided, is it? But we've got the parameters necessary. So let's switch to the calculator view and get this computed. So obviously we're going to use the time value of money worksheet, making some really quick inputs here. We're looking for PV. Now, the time to maturity is 3, so that's 3 for N. We've got the yield to maturity 8, so I've got 8 followed by I over Y. Now, the PV is what we're looking for. 100 is the future value, and the coupon is 6. So let's compute PV, and I can see that this brings an answer of 94.846, roughly. Good. Well, I'm going to need this input to have the Macaulay duration table or schedule set up, because we're going to do a bit of a table here. I'm going to say period, and I'm going to have the years 1, 2, and 3. Then the cash flow associated with each period. And because this is a simple 6% coupon bond, it's going to be 6, 6, and 106 at the end of the third year. Now, the next thing we need to do is turn these cash flows into PVs, into their present values. And we're going to obviously need to do a bit of discounting. Now, each of these cash flows will need to be discounted to its present value, but be careful using the rate that corresponds to the yield to maturity. So if the yield to maturity, which we're given up there, is 8%, we're going to be dividing the first year coupon by a factor of 1.08, this one by a factor of 1.08 squared, and this one by 1.08 to the power of 3. Obviously, on the calculator, you could easily do this using the cash flow menu. I'm not going to a cash flow worksheet. I'm not going to do that. I'm just going to take each one and say 6 divided by 1.08. That equals to 5.556. Especially as I want the individual numbers. So these are my 5s. I know they look like S's, but that's a 5. The next one, 6 divided by 1.08 to the power of 2. That's 5.144. And the next one, the big one, is 106 divided by 1.08 to the power of 3. 84.146, and you may have noticed that in order to raise to the power of 3, I was using the y to the power of x key followed by 3. Right. If we add these present values up, if we compute their sum, hopefully you know what we should get. 5.556 plus 5.144 plus 84.146. Well, I've got 94.846, which is actually the same as the value of the bond. Now, theoretically, I didn't need to compute this bond value, but I wanted to do it upfront so as to show you that doing the yield to maturity computation using the time value of money worksheet yields the same result as discounting the individual cash flows associated with the bond to their present values and then computing the sum. It's the same thing. Now, more importantly, I'm going to have the weight. And what I mean by this is the weight of each cash flow, each period's cash flow in the overall value of the bond. So to do this for the first cash flow, I'm going to take the 5.556 and divide that number by 94.846 to show that the weight of this first cash flow is 0.0586 in the overall value of the bond of 5.86%. I do the same thing for the next one, 5.144 divided by 94.846. This weight is going to be slightly smaller. It's 0.0542. It's slightly smaller than the previous one because it's the same cash flow in absolute terms, but in present value terms, it's lower because it's further away. And the final one, obviously, this is going to produce the highest component of the bond's value, so I'm expecting a very big weight here. Divide by 94.846. Okay, 88.72%, so 0.887. And I think if we add all of these weights up, just to check whether we get the expected result, 0.0586. As you can probably imagine, I'm hoping for a result equal to 1. But let's have a look, 0.8872. Yes, okay, perfectly equals 1, which means we've covered 100% of the bond's value. And look, for the very final step in the computation of something called Macaulay duration, I'm going to create the final column here, which is going to be period, i.e. 1, 2, or 3, times the weight. So for the first one, 1 times this equals 0.0586. Now for the second one, it's going to be 2 times 0.0542. Okay, the result here is 0.1084. And for the third one, it's 3 times 0.8872. 2.6616. Okay, now very importantly, we add these up. So this one plus 0.1084 plus 0.0586. And I see a result of 2.8286. Now, this is called Macaulay duration, and what it is showing us is the sort of weighted average in terms of the life of the bond. This is expressed in years, in terms of how long we need to wait in order to receive cash flows from the bond. And the cash flows here are weighed by their respective, the cash flows, that they are not weighed, but they help us derive the weights necessary to weigh the periods. However, Macaulay duration alone is not as useful as something called modified duration. And modified duration is the one that's going to help us assess how sensitive a bond is to interest rate movements, something that we will be doing in follow-on questions in the future as well, and something you should be doing in your curriculum studies anyway. So modified duration is taking the Macaulay duration, so what we computed just a moment ago, and dividing this by 1 plus r, where r is simply the yield to maturity on the bond. So I know this is 2.8286, and I'm dividing, because I know the yield to maturity on the bond is 8%, so dividing by 1.08 over here, let's see what the result is. 2.62 roughly. And this is modified duration. And this is an estimate. Let me write this down, although many of you will know this already. Estimate of percentage change in the bond value or in bond price given a 1% change in interest rates. So it shows us the sensitivity, interest rates, or basically the yield to maturity, which is a function of interest rates. But this yield to maturity is more precise in terms of scoring the points in the exam. So this shows you the sensitivity of the bond to yield to maturity shifts, which are a function of interest rates changing in the economy or in the environment. This is the useful measure which you will need across the fixed income curriculum, but it itself is a function of Macaulay duration, which your book presents as a computation that should be done like this. Hopefully you won't have to do it in the exam as such, but just in case, this is how you arrive at the figure. And 2.62 corresponds with answer B to this question.